Of all the physical sciences, one of the most popular is astronomy. I mean, who hasn't looked up at the night sky, wondering about the twinkling stars and the occasional meteor that flashes across the upper atmosphere? Since mankind invented the telescope, our wonder has only increased. With the Hubble telescope, we can look deep into the cosmos, seeing the birth of the very first galaxies in the universe. Looking at objects a little nearer, we see lovely spiral galaxies, majestic pinwheels, slowly twirling over the eons. It is by looking at spiral galaxies that this video's big mystery was first discovered. In the 1920s, astronomers first realized that the smudges that had long been seen on their photographic plates were actually collections of stars held together by gravity that we now call galaxies. Immediately, they began to apply Newton's law of gravity and inertia to predict the rate at which the galaxies rotated. The idea is simple. Just like planets orbit the sun, stars orbit the galaxy. These orbits are basically circular, and in order for a star to move in a circular path, it needs to feel a force. The force that causes this orbital motion is gravity. By measuring how the mass of the galaxy is distributed, you can calculate how much the galaxy tugs at each particular star. The equation we see here highlights the most important points. The force needed for circular motion is the force of gravity. The equal sign just says that they have equal value. The force it takes for an object to move in a circular path depends on the object's velocity. Just like an object tied to a string and spun in a circle pulls more strongly on the string, the faster it goes. The force felt on the star due to gravity depends on the mass of the galaxy. More mass means a stronger force. Finally, both forces depend on the distance from the center of the galaxy to the center of the star. These effects are well known, and anyone who's taken an introductory physics class will have seen them. Since we see that one side of the equation involves the velocity of the star and the other involves the mass of the galaxy, with a little effort, it's pretty easy to calculate what the known laws of physics predicts for the velocity of a star for different distances from the center of the galaxy. This relationship is shown here. Stars near the center of the galaxy orbit slowly, and the speed at which they orbit increases as the star's distance from the galactic center increases. Once you get far from the center of the galaxy, the star's velocity is predicted to again be slower. This is an easy calculation for astronomers to do, and there is no controversy about this prediction. So what is observed? Do the stars move as expected, or do they have a surprise for us? Well, stars near the center of the galaxy move with exactly the predicted velocity, with stars near the center of the galaxy moving slowly, and those further away moving more quickly. So far, so good. However, stars very far from the center of the galaxy do not move slower and slower as predicted from the theory. Instead, the measured orbital velocity of the stars is nearly independent of the radius of the orbit. This result is shocking. When you see a discrepancy of this magnitude, something is very, very wrong. No small tweak of your equations will explain the differences between calculation and observation. And since the calculation is so simple, it forces scientists to return to the very basics. So let's just take another look at the equation we just saw. The equation says that the force required to make a star move in a circle is equal to the force of gravity. Thus, we are required to conclude that either we don't understand the equations that govern circular motion, or we don't understand gravity, or these two forces aren't equal. There is no other possibility. Rather than using this equation, I'd like to use this image of a tree, which says the same thing, but in a way that's easier to understand. The roots of the tree are the various observations that show us we don't understand the motions of the heavens. There are many such observations. The rotation of galaxies is just one. The branch in the trunk shows the two big possibilities that we don't understand motion or gravity. Each subsequent branching is a different hypothesis. Over the last 90 years or so, possible explanations have been tested. We don't have time in a short video to explain all of the tests, but in 2013, one final hypothesis seems to explain all of the data. This hypothesis is that surrounding most galaxies is a huge amount of matter that is invisible. We call this matter dark matter. So what does invisible mean? Well, it obviously means that we can't see it with our eyes, But it also means that this matter doesn't emit heat, radio waves, or any other form of electromagnetic radiation. Perhaps even weirder, our best guess is there is 5 times as much of this dark matter as there is the ordinary matter that makes up you and me. 5 times. Do we have any evidence for dark matter beyond our astronomical observations? Well, no. The hypothesis of dark matter does a pretty good job of explaining these cosmic anomalies, but it would be good to detect this dark matter in a more direct way. Because the identity of dark matter is one of the big mysteries of modern physics, there are many experiments trying to find it. Experiments located a kilometer or more underground in abandoned mines search for dark matter that should be passing through the Earth. Experiments on satellites probe the heavens looking for the signature of dark matter particles occasionally interacting with each other. And scientists at particle accelerators are trying to actually create dark matter in the laboratory. Several of the experiments have seen hints that suggest that they've seen dark matter, but others haven't. Until several experiments begin to tell a common story, nobody should believe the dark matter hypothesis has been proven. Still, the evidence is very strong, and a big push is on to solve this mystery once and for all.